Now we will consider a simplified case of one-dimensional diffusion, which basically means that Peclet number is much smaller than 1, or in fact is simply equal to 0, right? So here we are assuming that u is 0. That actually means that Peclet number is greater than is equal to 0. So we are considering this case, and also we are focusing on one-dimensional diffusion for just for our analysis. Okay, so let's consider this is the porous media. This is one-dimensional medium. So this is close this side. This is close this side. Okay, and we consider that concentration is equal to 0 everywhere originally, and this is simply, let's say this is water. Okay, and now we supply a constant concentration boundary. From here, let's assume that C equal to C naught, and we maintain that concentration at the left boundary. Okay, and in the beginning, and this is at time t equal to 0, your concentration is 0 everywhere, but it's equal to C naught at the left boundary, right? And now with time, increasing time, so this is time increases, so this is, let's say, t equal to t1, t equal to t2, which is greater than t1, t equal to t3, which is greater than t2 than t1, right? And we maintain the left boundary here equal to C naught, C naught, and C naught. So you can see with time, this solute that from the left boundary slowly diffuses into the medium, and it takes more and more space with this concentrated profile. Okay, whereas at the right boundary here, C is still equal to 0. But anywhere here in between, you can say that C here is smaller than C naught but greater than 0, right? So that is the mixed concentration, which has value between 0 and C naught. All right. So now let's try to find out how does this mixing happen, what is the length scale, what is the time scale of this mixing. And to be able to model this, we will use the advection dispersion equation that we have already considered before. So we will use this equation. Okay, and remember that we are considering 1D problem with no velocity, right? And that is why all the terms with velocity will go 0, this goes 0, this goes 0, this goes 0. And this is a 1D problem. We are assuming it's only happening in x direction. So let's consider that this is our x-axis, right? In that case, this term will become 0, right? And what we are left with here are dc over dt is equal to d by dx, dc over dx. All right, and remember that we are assuming Peclet number to be equal to 0. That actually means that d must be equal to that must be equal to dm effective. Okay, and for now we will write dm effective to be simply equal to dm, assuming that tau is equal to 1. Okay, so this is an assumption, but whatever result we derive can be used for dm effective by assuming different value of tau. Alright, and now because dm effective is simply equal to dm, so dm can be considered constant, and this is not a function of x, and that's why we can take d outside the derivative, and then the equation will become dm d square by dx square c. Okay, so this is the equation we are trying to solve, where c here is the solute concentration, right? And we have an initial condition here. And what is that initial condition? We know that before the flow started at t equal to 0, right? Concentration is 0 everywhere at all points in x. And that is why the initial condition, which basically means at time t equal to 0, says that c equal to 0 everywhere. Okay, that is the initial condition. And then we have boundary conditions. Okay, now what is the boundary condition? And here for boundary condition we are focused more on the values greater for t greater than 0, because that is when we apply the boundary condition. And looking at this setup, you can say that at x equal to 0, c is always c naught, right? As we are measuring x from here, x from this location, and x equal to 0 here. So at x equal to 0, you are maintaining a concentration of c naught. And as you go further into the x, so let's say x tends to infinity, right? Here you go further right and x tends to infinity. So if you keep supplying c equal to c naught, so mixed zone will become broader and broader, or you will get larger and larger mixed zone of solute with water. But as you go to infinity, your concentration will still remain equal to 0, right? Because we are talking about an infinity point. So as x tends to 0, your c will always be equal to 0, because that is at infinity, and your solute cannot reach the infinity, right? And that is why we have these two boundary conditions. At x equal to 0, concentration is c naught, and x equal to infinity, concentration remains 0 at all times. Okay, so here c equal to c naught at x equal to 0, and c equal to 0 at x tends to infinity. Okay, so these are two conditions we have. And now you can see we have one equation and two variables. So one equation on c and two variables are x and t. So it is difficult to solve one single equation with two variables, and that is why we will use a technique called similarity solution to find a solution to this equation. Okay, because one single equation we cannot, using just this partial differential equation, we cannot get solution. Okay, so we will derive a similarity solution for the problem. Okay, and this similarity solution is also known as the dimensionless solution. Also known as self-similar dimensionless solution. Okay, so basically what the solution we are going to derive for this problem is a dimensionless solution, and then from the dimensionless solution we can predict the dimensional solution backward. Okay, so we will first define a dimensionless concentration. Okay, so let's assume that we have a concentration that we define as C hat, and that is divided by C naught. So C naught is the maximum concentration we know, right? That is the injected value, and concentration anywhere else must be smaller than C naught. That cannot be greater than C naught, right? And that's why we divide C by C naught, and that is why this C hat now varies between 0 and 1. So at the injection point, C hat is equal to 1, and at other points at the other side of the domain, C hat will be equal to 0, right? So now if we use this equation, if you look at this equation, this says that this is d square C by dx square. So if you divide both sides by C naught, where C naught is a constant, right? C naught is a constant. It can simply be brought inside the derivatives, and this will give us C hat over dt d square C hat over dx square. All right. So this is a dimensionless form of concentration we get, but T and X are still in dimensional form. So now we have to find a new dimensionless variable that represents time and length scale. Okay, so for finding dimensionless variable, to find a new dimensionless variable, we use scaling analysis. Okay, and this is something we have done previously in the course, and that's why I'll not go into the detail. But what we can do here is we can write C hat by T is dimensionally equal to d C hat over x square, right? So dimension of C hat by T must be equal to d times C hat by x square, and that is coming from this equation, obviously, right? This is dimensionally equivalent form, and that's why I write equivalent at the for equating this equation rather than simply writing the equal sign. All right, and what you see here is this cancels with this one, and that is why this becomes x square is dimensionally equal to dt. Okay, so x square is equivalent to dt. So what we can do now to be able to find or to be able to convert this into equal sign, we must add a numerical value, right? Then only it will be equal to, then only we will be able to say that apart from being dimensionally equal, they are also numerically equal, right? So let's first also convert this into dt. So x is equivalent to square root of dt. So here what we do, we add a parameter called eta, okay, and also a factor of 2, which we'll discuss why. So this gives us a parameter called eta that is defined as x over 2 dt, where eta here is a dimensionless variable that combines both x and t, right? So what you see here is this is a single variable, eta is a single variable that now gives you the effect of both x and t, right? And this is a dimensionless in value. And now you will ask how we went from here to here. So at the moment we don't know the value of eta, right? We are just saying that eta is a dimensionless variable. It may have different constant or different values. For that particular value, this x must be equal to square root of 2 dt. And now because eta is something we want to define, this factor of 2 that we have included in the square root, that is just for some mathematical simplification, which will become clear in coming derivations, and that does not really affect our dimensions. So we simply add it for some simplification, which will become clear in future in incoming derivations. Okay, so here we have defined eta, which is also known as a similarity variable. Okay, so now we have defined eta, so we can further simplify this equation by doing change of variable. All right, so what we will do is, because now eta is a single variable, we can write this as dc hat by d eta is becomes d eta over dt is equal to d. So this one is basically dx dc by dx So here again we will for the right side as well we will do this. So this equation will become dc hat d eta over dt is equal to d over d eta dc hat over d eta. Wait, I am making this mistake here. d eta by dx d eta by dx. Okay, so we have just done the change of variable from that equation, previous equation, to here and then to here. So x and y has been changed into eta, a single variable, right, which is basically dimensionally and also numerically consistent now. All right, so now we know eta is already defined in this way. So what we can do is we simply replace eta with that. So x over 2 dt d eta over d eta dc over d eta and d by dx x over 2 dt d by dx x over 2 dt. All right, so this is quite a straightforward. We have just replaced eta with the formula that we derived here. All right, and now what we do, we simplify this equation further. So this one we can differentiate with respect to t. So this will become 2d minus 1 by 2 t to the power 3 by 2. So remember, there is a factor of it has a factor of t to the power minus 1 by 2, right? And if you differentiate it, this will give you this equation. In this side you will get d square c hat over d eta square, and this becomes 2 dt times 1 over 2 dt. Okay, because your x here cancels out. If you differentiate this with respect to x here, this with respect to x here, that comes out. And t is not a function of x, remember, right? So you are differentiating it with respect to x. So basically t is a constant in x. They are independent variable. So x and t are independent variables, and that is why t behaves like a constant for x, and that's why this can simply come out of the derivative, right? And in this way the equation that you get here is this. So minus 1 by 2 dt. So here t has a factor of t to the power 3 by 2. So we will take t to the power half inside the square root, and you can write it something like this. And in the right hand side you get d square c over d eta square, and this becomes 2dt. Alright, so this is what we have got so far, and now we can simplify this further. So here this d cancels with this one, and t here cancels with that t, and this 2 cancels with that 2, right? And now you can see this factor of 2 is nicely getting cancelled, and that is the reason why we had added a factor of 2, because if we don't add factor of 2, eventually we will stuck with a factor of 2 in the equation. Alright, so now the remaining equation we have is minus x over 2 dt d c hat d eta is equal to d square c hat over d eta square. Alright, these are the remaining terms we have, and now if you see carefully, this particular thing that you have here is actually equal to eta, right? That is how we have defined eta here, and that is why this equation can further be simplified. It will become eta d c hat over eta is equal to d square c hat over d eta square, right? Indirectly this gives you d square c hat by d eta square plus eta d c hat over d eta equal to 0. So this is the ODE that we have got. So here you have one single variable and one single parameter. So c is only a function of eta. Right now it's not a function of x and t separately. There is just one parameter and one variable. Alright, so it's quite a straightforward. So this is the governing equation we have got, and now because it's a double derivative or second order equation, we need two different conditions or boundary conditions for c in eta. Okay, so we can go back to the equation that we have derived, or conditions that we have used before, to find what are the values of c hat for different values of eta. Okay, so let's first recall what is eta here. Eta is x over 2 dt, right? And if you go back to the initial and boundary conditions, that says that at t equal to 0, your c is 0 everywhere, and for t greater than 0, c is c naught at x equal to 0 and c equal to 0 at x tends to infinity. Okay, and that is why we can use those conditions and find the criteria for c hat with respect to x. So at x equal to 0, c is always equal to c naught. That actually means that at x equal to 0, eta must be equal to 0 because x is 0. That means that your c hat is equal to c naught over c naught, because c is equal to c naught, and that we divide by c naught, so that becomes equal to 1, right? So at eta equal to 0, your c hat is always equal to 1. So that is one condition we have, right? And as x tends to infinity, c is equal to 0, or as at t equal to 0, c is equal to 0 everywhere. So both these conditions, if you put in this equation, eta equal to x over 2 dt, this actually means that your eta tends to infinity, and there your c hat should be equal to 0 over c naught, that should be equal to 0, right? So this is the other condition you have, right? And that is why now we have one ODE that is given here, and we have two boundary conditions that at eta equal to 0, c hat is equal to 1, and eta tends to infinity, c hat is equal to 0. So this is the condition we have, and this is the equation. Okay, so we are going to solve this equation with the help of these left conditions that we have. Okay, and that is what we will do in this in the next lecture.